Hello, everyone. Welcome to the final video on question 10. We're going to cover parts G, H, and I. So for this part, assume that the original graph is fully connected and that the vertex is incident to at least one negative edge. Okay. We then modify the original graph by multiplying each edge by -1, and then we run Kruskal's. So we can imagine a lot of scenarios in which this is not going to result in a valid MST for the original graph. So the question is that, we kind of saw these in previous parts. Well, if you want to imagine a quick scenario, just take like a 3-node thing, and it's like, I don't know, -1, 0, and 1. We multiply everything by -1. Previously you would have picked these two. Now you're going to pick these two, right? You're going to pick the other edge that you didn't pick before. Okay, so the question is like, are there any scenarios in which like we actually will still have the same MST? So in order to think about them, I invite you to think about the smallest edge. Okay. It's always used in the MST, right? That's just how Kruskal's and in general MSTs work. You're always going to use the smallest edge. Okay, now after you do this, the smallest edge becomes the largest edge. Okay, by the way, I want to point out that the logic I'm about to present could in theory be applied to previous parts, but this is where it wouldn't apply. Okay, the smallest edge becoming the largest edge didn't hold up for previous parts because those, not only the negative edges were multiplied by -1. So you can have a positive edge that was originally positive and it was way bigger than any, like the absolute value of any of the negative edges. Okay, so this only applies to this part where you multiply everything by -1. Okay, now the smallest edge really is the largest edge. Okay, so because the graph is fully connected, we don't actually have to use that edge, right? Because there are like, there's literally every other possible edge that you can use apart from that one. And because all the edge weights are distinct, right, they're all smaller than that edge. So you literally will not use that edge. You will use any other edge that you possibly can to connect everything together because every other edge exists. So you have all of the other options available to you. Okay. So because of that, we are not going to use that edge, but that's a problem because that was the smallest edge, right, that we used in the original MST. So the resulting MST is going to be different. And thus we'll never get the valid MST for the original graph because we're never going, like, will never use that smallest edge. So yeah. So that's that. That's 10G. Now 10H. Okay. So for this part, assume that the graph is not fully connected, and then we modify it by going through every pair of vertices that doesn't have an edge, and then we add an edge with weight equal to the weight of the largest edge, and then we run Kruskal's. So for this one, I think it's good to look at an example or some drawings. Okay. So let's just start off with our good friend, this thing. Well, actually, okay. We start off with this thing, right? Our classic like little triangle. And I'm going to add another vertex here. Okay. So I'm just going to arbitrarily fill this in like 1, 2, like 0. Okay. So the MST for this one, just to like get this out of the way, is going to look like this, right? 2, 1, and 0. Okay. If I now go through every pair of vertices and add the weights with largest possible thing I can add, it's going to look something like this. 0, 10. So here's the original one. Okay. Then I add a 10 here and a 10 here. Okay. Well, clearly the MST is still the same, right? We're still going to get that original thing. Okay. Because we're not going to use any of these new 10 edges because why bother? Okay. But what if I now had a slightly different thing? Okay. It's like, the question is like, can we break this? Can we find a way in which actually the original MST, a way in which like we won't find that the the original MST is not found? Okay. Let's go ahead and look at that. So what if I change this to be like that? So it's now 100. So this is actually the largest edge now. And I go ahead and make the modification. So, okay, remember, right? The MST for this is still going to be the same, actually, right? Because we have to use this 100 edge. There's no way around it. It's the only thing connecting that like lone solitary vertex. Okay, so let's go ahead and run the procedure we described in the problem on this. Okay, and this immediately leads us to our problem. We can use any one. Okay, so at the end of the day, we're going to have this like a little core of like 2 and 1, right? But the question is, how do we connect it to the last vertex? We have 3 choices, and they are all the same weight. So Kruskal's will pick just one of them at random or by some tie-breaking mechanism or whatever. Actually, I think it's random for this problem. Anyways, so it'll pick one of them at random. And that is a big problem because we only have a 1/3 chance of actually getting the valid MST. We have a 2/3 chance of not getting the original MST because one of those options is equally as good. So it's very probable that we actually won't get a valid MST. But well, regardless of whether or not it's probable, it's possible to not get a valid MST. We'll just have one of these like other edges, and they just don't. Those edges literally don't exist in the original graph, so they can't be a valid MST for it. So in other words, we conclude that H sometimes a valid MST, but it doesn't have to be in certain cases. So yeah. Now we move on to the last part of this question, part I. So for this part, again, we assume that the graph is not fully connected, and we modify it by going through every pair of vertices without an edge between them, and we add an edge with weight equal to the weight of the smallest edge, and then we run Kruskal's on the modified graph. Okay, so clearly we can think of examples in which this is going to produce an invalid MST, right? Because Kruskal's will want to prioritize those smaller edges, so it's going to want to use those in generality. And yeah, you can come up with an example of that. So the question is, does it sometimes, can we get a valid MST out of this still? Okay, so let's think about it. So the graph isn't connected, okay? So we're guaranteed that we're going to add an edge. By the way, I should mention, this problem reduces down to, are we going to use that new, any of these new smallest edges, right? Like, are we ever going to, like, is there a scenario in which we won't use them? Okay, so the graph isn't connected, so we're guaranteed that we're going to add at least, or isn't fully connected. It's not fully connected. So we're guaranteed we're going to add at least one new edge. So the question is, do we have to use that one new edge? Well, when do we use it? Okay, the answer is always. Okay, because it always will connect two new vertices together that they weren't directly connected before. And because of the way Kruskal's works, we're going to look at the edges in order of their weight. So that is going to be one of the first edges we look at, okay? And you know, the only way in which it like Kruskal's won't add that edge to the MST is if those two vertices were already connected together, okay? But remember, like we caught all the edge weights are distinct, so there was only one edge before that had this weight. So, and that edge didn't connect those two vertices together. So if those two vertices are connected together, that means that there was some other new edge that we added to the graph had to connect them together. So in other words, the new copy edges are always going to connect something new together, and we're always going to use at least one of them. So yeah, so we'll never get a valid MST because those edges don't exist in the original graph. So yeah, this never leads to a valid MST. And so yeah, and so that is actually the conclusion of question 10. That's all of the parts. So thank you so much for watching, and I hope that these videos were helpful. Ciao, ciao now.